Okay.
Welcome everybody to today's meeting of the online CUNY Set Theory Seminar. We are very pleased to have Eyal Kaplan from Tel Aviv University, a student of Moti Gittik, who will be speaking about some joint work he's been doing with Moti on non-stationary support iterations of Prikry forcings and restrictions of ultrapower embeddings from the generic extension to the ground model. Take it away, Eyal.
Thank you very much. Please tell me if you can't hear me or if my handwriting is not so clear. So let me describe the motivating questions, and they are quite general. So assume that we have a forcing notion and let's take a generic extension for it. So we take a generic set G over the ground model V. And in VG, let's assume that we have a measurable cardinal. And assume that this is witnessed by a normal measure on kappa. So W in VG is the normal measure on kappa. So we may consider the ultrapower embedding, let's denote it by JW, from VG to a model of the form MH by elementarity. The target model is going to be a generic extension over some ground model M with a generic set which is the image of G. And let's ask the following questions. So the first question, in both those questions, we consider the embedding JW when restricted to V. It's an elementary embedding from V to M. And we ask first whether this embedding, is it definable in V? Is it a definable class of V? And another question we can ask, regardless of the answer to the first question, is JW restricted to V? Is it an iterated ultrapower? Of V by measures or more generally by extenders. So those are quite general questions, and we're going to deal with them in a very specific context. But there are things that we can say in general. So by work of Hampkins on gap forcing, if the forcing P has a gap below kappa, in a sense that I'll define in a second, then JW restriction to V is definable in V. Now, when we say that the forcing P has a gap below kappa, we mean the following. So P has a gap at delta below kappa if it can be factored to the following form, an iteration P1 and then P2 where P1 is non-trivial, has cardinality below delta, and it is forced by P1 that the forcing P2 is closed enough, is delta plus 1 strategically closed. So under those assumptions, Hempkins proved that when we take an elementary embedding in the generic extension and restrict it to the ground model, it's going to be definable. By the way, if there are any questions or remarks, you can ask during as I speak. It doesn't matter for me.
Eyal, I have a basic question.
Yes.
In your general setup, it's possible that M is not even contained in B, right?
Yeah, in the general settings, yeah.
Okay.
So, and even if it is, by the way, contained in V, we don't assume, we don't know whether it is a class of V, whether it's definable in V or not.
Right.
Should we be assuming that all these, that V is a standard model, is a transitive set?
That V is a transitive set?
No, it's a standard model. It's a well-founded model.
Yeah. And MH was the transitive collapse of the ultrapower. As for the second question, so there is a general result of Schindler. So if there is no inner model with the Wooding cardinal, and we force over the ground model, which is the core model, then the answer to the second question is positive. JW restriction to V is an iteration of V by extenders. But we did consider those two questions in a context where those pair of general results cannot be used. So our original goal was to get a model where, let me write it. So I want to get a model where kappa is strongly compact, the least measurable, and carries a unique normal measure. So the standard way to get the following, the first two things, strongly compact, which is the least measurable, is to iterate, to apply a Megiddo iteration of Prikry forcings, iterate Prikry forcing forever measurable below kappa, preserving strongly compactness of kappa. This iteration, the Megiddo iteration of Prikry forcing, and in general many other iterations of Prikry type forcings, such iterations don't have a gap, don't have gaps. When you take quotient of such forcings, they are not closed enough. And as for the second question, we want to apply this forcing in the presence of large cardinals, strongly compacts, super compacts, and we can't rely on it as well. So we needed to develop tools to avoid the core model theoretic aspects
Excuse me,
that
could you maybe explain, could you motivate this goal more clearly? I don't really understand why that is the goal after you stated the first two questions.
Well, actually, this was the goal, and then we stated,
Okay.
after studying this, we stated the first two questions. So maybe
okay.
this is the original goal, and the second questions were somehow,
They came
we
up.
somehow got to them from that. But
I see. Okay. Thank you.
Okay, I thought you meant to motivate the goal itself, which is a strong separation between strongly compacts and super compacts. Super compacts have many.
Yeah. No, I see the intrinsic interest of this goal. Yes, definitely. But I just didn't see the connection to the questions. That was all. Okay.
Okay. So yeah. So I'm going to give the connections. So just before I said that, there is in order to achieve this goal, we need to iterate Prikry forcings, destroy measurability of every measurable cardinal below kappa. In order to control the normal measures in the generic extensions, one of the tools that will help us control the normal measures in the generic extensions is to use a support which is not the non-stationary support, not the standard full support iteration of Prikry forcing, but the non-stationary support. This is why we consider it in the we consider the non-stationary support in this talk, even though most of the results can be generalized to the full support iteration. So the way to achieve this goal is to iterate, and we're going to describe this forcing, to iterate with the non-stationary support, destroying each measurable cardinal below kappa. And after that, in the generic extension, we will still need to use some tools in order to argue that there exists a unique normal measure in the generic extension. So so let's describe this in a bit more in more details. Let me describe first the forcing.
Well, can I say something first?
Sure.
So I think that your goal, you want to get this starting with a super compact and just one super compact, because Goldberg and Wooden can take a measurable limit of super compacts, and if they assume the ultrapower axiom, they get this goal. And in fact, you can even do that, of course, as is found in the first of your two papers with Moti. You can even do this with the Magidor iteration of Prikry forcing. But what's different here is that you're not using a measurable limit of super compacts or strongly compacts, the same thing, assuming UA. You're just using one super compact here.
I think but the main thing is that we want it to be the least measurable, so we don't.
Right, but you can do that with a measurable. If you have a measurable limit of super compacts or strongly compacts, and you have the ultrapower axiom, and you do the full support iteration, it's the least measurable, the least strongly compact, and it has only one normal measure. So the goal, at least according to my correspondence and discussions with Moti, is to do it not with this strong an assumption, but using just one super compact.
Yeah,
that's,
so we're going.
That's the difference. And also you're going to need to have a restricted universe, but I know you're going to get to that.
Yeah, we're going to start with the super compact, and we're going to assume an assumption weaker than the ultrapower axiom, even though the ultrapower axiom suffices here, and that is a uniqueness of measures of order 0 at each of the measurable cardinals.
And you're also assuming no measurables above or no inaccessibles above. You need an anti-large cardinal hypothesis.
Yeah, but we can chop the universe above kappa if we want. I mean, This
Right.
is
Right, but you do need some kind of anti-large cardinal hypothesis. And that's very important here, because if you do it with a measurable limit of supercompacts, you don't need an anti-large cardinal hypothesis. So there's a bit of a difference there.
yeah, okay. So thank you for this remark. So let's present the forcing. So let's assume throughout this pair of talks, assume that kappa is super compact. We don't even need that in order to state the forcing. Let's assume that kappa is a measurable limit of measurables. When we apply this forcing to get these goals, we will need to change the assumption to strengthen the assumptions on kappa. So assume that kappa right now is a measurable limit of measurables. Let's assume as well that GCH holds below kappa throughout this pair of talks. And let's define the forcing. So we define an iteration P alpha Q beta of length kappa. And an iteration of Prikry forcings. Let's state it like that. So for every alpha lesser or equal than kappa, and for every p in P alpha, I want to define exactly what do we mean by the non-stationary support. But before that, every condition in the forcing P alpha is a function. The domain of P is alpha. For every beta below this alpha, P restriction beta belongs to the forcing up to stage beta, and P restriction beta forces that the value of P at beta belongs to the forcing Q beta. Those are the standard things. We want the forcing up to alpha to force for every alpha which is measurable in V. If alpha below kappa is measurable in the ground model V, we want the forcing up to stage alpha to force that Q alpha is the Prikry forcing using a normal measure let's denote it by U alpha star. I will explain this notation in few minutes. This is the name which depends on the first alpha, on the iteration up to stage alpha. This is the name for the normal measure on alpha, which is used at stage alpha to singularize alpha. And about the non-stationary support, we want the following. And by the way, if alpha is not measurable, we just want Q alpha to be the trivial forcing. Q alpha is forced to be trivial.
Eyal, you are assuming, so alpha is measurable in V. What if this is killed by P alpha and there is no longer a measure there?
We're going to justify if alpha is measurable in V, it's going to be measurable in the generic extension up to alpha.
Ah, okay, good.
About the non-stationary support. So for every alpha lesser or equal than kappa inaccessible, Again, I'm stating when a condition P belongs to the forcing. So the condition P should have a non-stationary support. The set support of P intersection with alpha, which is the set of coordinates beta below alpha for which P restriction beta forces that P beta is empty, is that beta that the forcing doesn't do anything at beta. This set is non-stationary in alpha. So we have clubbed many places in which P doesn't decide anything. Oh, and we should define the order. So
It should be different than empty set, right?
Yes.
support of P, yeah, it's the places
Yes.
where, yeah, thank you. Let's define the order. So if we have a pair of conditions P and Q in the iteration up to stage kappa, we say that Q extends P. Hopefully this notation will not cause any confusion. So Q extends P if the following hold. So we want to extend the support. The second thing, inside the support of P, for every alpha in the support of P, we want Q restriction alpha to force that Q at coordinate alpha extends in the order at stage beta with stage alpha, P at stage alpha, and we want the following condition. We want a set, a finite set inside the support of P, such that for every alpha in the support of P outside this beta, we have this extension is direct. So Q restriction alpha forces that Q at coordinate alpha direct extends P at coordinate alpha. So inside the support, when we wish to extend the condition, we may take only finitely non-direct extensions. And by the way, outside the support, we can take as many as we want non-direct extensions. And if this set B is empty, then we say that Q is a direct extension of P. And we denote it by Q extends star P. Okay, so this is the forcing, and let's recall some of its properties. And the main thing we want to consider is what are the normal measures in the generic extension. Before that, let's briefly recall some of the more basic properties of this forcing. So this forcing satisfies, when we write P, the meaning is to the iteration up to stage kappa. So it satisfies the Prikry property, so every sentence in the forcing language can be decided by taking a direct extension over any condition. And Another property that is that holds typically in non-stationary support iterations, let's call it the fusion property. So what is this fusion property? Assume that we have a condition P in our forcing, and for every Xc below kappa, Xc is a name in the forcing up to stage C, including C, such that P restriction of up to Xc+1 forces that Xc is dense open with respect to direct extension. Then there exists P star direct extension of P and the club C in kappa, such that for every C init, P star restriction to Xc+1 forces that the part of P star above Xc+1 enters Xc. So what we have here, we have for every Xc below kappa a name for a dense set in the quotient forcing above Xc, a set which is dense open with respect to direct extensions. So we say the following: we can start from a condition P and direct extend it such that many of its final segments enter those dense open sets, club many of the final segments. Okay, so and we should say at this point, this property, it appeared in many other forms. I think it appeared originally in the work of Friedman and Megidor, where they used the non-stationary support in order to control the number of normal measures. So we're going to use similar ideas. Another
Sorry,
property.
no,
Yeah.
in which forcing is Xc dense open?
In the tail, right? In the quotient forcing after Xi+1, it seems.
Oh yeah, I didn't write that. Yeah. Xc is subset for the tail forcing, so maybe. Xc is a subset of the forcing above Xc, not including Xc.
Okay.
Yeah, thank you. And so another property. So, and here we assume GCH throughout, but let me recall, we assume GCH, P preserves cardinals. And another property, which might be maybe less known. So assume that alpha is a P name of an ordinal. Assume that this is forced, or we have a condition P in the forcing. Then there exists a direct extension of P. We cannot hope to decide the value of alpha, but we can decide it up to less than kappa many possibilities. So we have a direct extension P star of P, and a set A in V of ordinals of cardinality less than kappa, such that P star forces that this alpha belongs to A. And note that we don't assume that alpha is below kappa or something like that. Alpha is any ordinal. The set A has cardinality below kappa, but it may contain ordinals above kappa. This property is going to be a key when we describe the restriction of JW to V as an iterated ultrapower. So when we will use it, I'll remind you this property. And the last property of this forcing, P does not add fresh subsets to kappa and to kappa plus. The fact that the forcing does not add fresh subsets to kappa and kappa plus, the fact that it doesn't add fresh subsets to kappa is very similar to the standard full support iteration. The same reasons for both forcings show that there are no fresh subsets of kappa, but for kappa plus there is a difference. This non-stationary support complicates the argument, and we needed some ideas from Hampkin's gap forcings in order to prove that. But I want to invest our time in other things. So I just should say that the proof for the fifth property for the standard full support iteration is much simpler than the non-stationary support. So the plan is as follows. So first, we want to characterize all the normal measures W in VG. Once we do that, this will be enough to settle our original goal, which was to get a model where we have extremely compact, the least measurable, with the unique normal measure starting from a super compact, and some assumptions about the ground model. But this opened the path for the following things. So given W and VG, we can prove that JW restriction to V, or let's say it like this, we're going to describe JW restriction to V as an iteration of V, iterated ultrapower of V. It's going to be an ultrapower taken by normal measures only. And after that, we're going to discuss the definability of JW restriction to V. So we can provide a simple sufficient condition for definability of JW restriction to V as a class of V. So the second and the third points are my main goals in this pair of talks. But in order to start characterizing the restriction of JW to V as an iterated ultrapower, we need some of the things. We need the characterization of normal measures in the generic extension. So I think today we will focus on this characterization. Maybe we will start describing the structure of JW restriction to V as an iteration of V. And next time, focus mainly on those 2 points. Okay, so as for the normal measures on kappa in the generic extension. So let's see the characterization. So assume first that U is a normal measure of order 0, Mitchell order 0 on kappa in V. We can define now in the generic extension with our forcing P, we can define a natural extension of U. U star will be the set of values of names A for a subset of kappa, such that for some P in G, JUP forces that kappa belongs to JU of A. So we take the values of names such that some condition P in the forcing satisfies the following. In MU, in the ultrapower taken by U, the normal measure on kappa over V, the condition JU of P forces that kappa belongs to JU of A. And this U star is a normal measure on kappa in the generic extension. This is one direction. Moreover, every normal measure W in VG on kappa has the form U star for some U and V with Mitchell order 0. Was there a question?
No, I don't. I think it was just background noise.
Just a remark about this definition of U star. The fact that this U star is going to be a measure, the fact that it is an ultrafilter, this is where we heavily use the non-stationary support. So such U star can be defined with the standard full support or with the Easton support iteration, but it's not going to be an ultrafilter. Conditions of the form JU of P, where P belongs to G, are not enough to decide all those statements for all the possible names for subsets of kappa. We're going to need to take direct extensions. For instance, in the full support iteration, we're going to need to take direct extensions of such conditions above kappa in order to decide all those statements. So the significance of the non-stationary support is that U star defined this way is actually an ultrafilter in the generic extension. And the reason behind this is the fusion property. Okay, so let's see the proof. There are many things which are standard here. Let's show at least for the first part, that U star is the normal measure on kappa in the generic extension. Let's show that it is an ultrafilter, a kappa complete ultrafilter. So we can do both those things in the following way. So assume that P is a condition which forces that a sequence A alpha for some alpha less than delta, for some delta less than kappa, is a partition of kappa. We're going to use fusion and direct extend P. This is going to be a density argument, so we will take this direct extension inside G, such that the direct extension witnesses that one of those sets, actually it's not going to be a direct extension, it's going to be an extension of P, not necessarily direct, because there will be several steps in the extension, but this extension will witness that one of the sets A alpha belongs to U star. So we're going to apply fusion. Let's define the set for every C in the interval between alpha and kappa. Let's consider X's which are high enough. Let's define XC. All the conditions in the forcing above Xc plus 1, which decide to each of those sets in the partition Xc belongs. So for some alpha star less than delta, our forces that Xc belongs to A alpha star. We have the Prikry property in the quotient forcing, and we have direct extension in the quotient forcing, which is enough in order to decide whether Xc belongs to each one of those sets. So there exists some alpha star. So there exists some, by taking the direct extension of conditions above Xc, we can find such alpha star. So Xc is dense open with respect to direct extensions. And we can apply fusion. We can do this in a dense way above P. So we can assume that the condition obtained by fusion belongs to G. We have P star, direct extension of P, inside the generic set G, and the club C in kappa, such that for every Xc in this club C, P star restriction to Xc plus 1 forces that the final segment of P star enters Xc. Namely, it forces that for some alpha star below delta, P star above Xc plus 1 forces that Xc belongs to A alpha star. Now, let's take advantage of the fact that this club C belongs to U. So in MU, in the ultrapower taken with U, we have the following. We may consider, I'll write it in another way in a second, but we may consider the condition Ju of P star up to kappa plus 1, and it forces that for some alpha star, again less than delta, Ju of P star above kappa plus 1 forces that kappa belongs to Ju of A alpha star. Now, what is this condition, Ju of P star restriction to kappa plus 1? In general, U was taken with Mitchell order 0, so kappa is not immeasurable in MU. So this is just the condition P star. We don't have a forcing over kappa. And by the way, even if we had, even if U wouldn't have Mitchell order 0, still this condition was free at coordinate kappa because of the non-stationary support. Kappa was outside Ju of the support. But this condition is more or less this P star, which forces the existence of such alpha star below delta. And now we just extend P star inside G by extending P star inside G. We can assume that it decides the value of alpha star. So what did we get? We get that for some alpha star below delta, the condition P star followed by its image above kappa force that kappa belongs to Ju of A alpha star. And this is exactly what means that the value of A alpha star belongs to U star. So this is the argument behind the kappa completeness of U star, and this very similar argument shows that U star is normal. And let's move on to the other direction. So the other direction, in the other direction, we have W in VG, a normal measure on kappa. Now we want to prove that W has the form U star for some U and V of mutual order 0. So I'm going to write here a claim. Let's prove this claim at the end. If we denote by U the intersection of W with V, it belongs to V. We will prove this in a few minutes. Let's just proceed from this point. Let's assume that this U indeed belongs to V. Note that it has mutual order 0. Otherwise, W would concentrate on the set of former measurables in V, which are now singulars, and W is normal. It cannot concentrate on cardinals of cofinality omega. So indeed, this U has mutual order 0, and let us argue that U star is indeed this W. And in the proof that this U star is W, we're actually going to start decomposing JW restriction to V. How? So we first start with the set X in U star, and we can fix a name for it, and the condition P in G be such that Ju of P forces that kappa belongs to Ju of the name that we fixed for X. We want to prove that this X belongs to W. So we're going to take this formula and transfer it to the target model of JW when restricted to V. So recall that JW from VG to MH is the ultrapower embedding of W in VG, and JW restriction to V is an embedding from V to M. Now we can define an embedding K from MU, the ultrapower of V with U, to M. So K maps elements, standard elements in MU, which have the form JUF on kappa, to JWF on kappa. Namely, K maps the equivalence class of a function f modulo u to the equivalence class of the same function modulo w for every f in V with domain kappa. And the fact that W extends U shows that this K is elementary. Right, so we have, for instance, the equivalence class of F modulo U belongs to equivalent class of F prime modulo U. This holds if and only if the set of X's for which F of X belongs to F prime of X belongs to U, but U is the intersection of W with V. So in the generic extension, we have the set of X's below kappa, such that F of X. Okay, so in the generic extension, we have the equivalent class of F modulo W belongs to the equivalent class of F prime modulo W. So M witnesses this, since for every X, V witnesses this. So K is elementary, and it's not hard to see that JW, when restricted to V, is K composed with JU. We just apply JU on an element of V. This is the equivalence class of the constant function, and K maps it to the equivalence class of the same function, just modulo W. And this is how JW restriction to V will act on an element of V. So this is the first step in the in the decomposition of JW restricted to V to iterated ultrapower, and we will get back to this K. But how can it be used? So we call, what did we have? We started from some X in U star, we picked a name, and we picked a condition P in G, such that JUP forces that kappa belongs to JU of the name. And now we apply K on this formula, and we get that JW of P forces that K of kappa, which is kappa, both ultrafilters U and W are normal, and kappa is represented by the identity function, belongs to JW of the name. Now, since we took P in G, JW of P belongs to H, which is the image of G. So in MH, we get what we want. Kappa belongs to the value of this name with respect to age, which is just the value of X under, not the value, the image of X under JW. So this proves that every normal measure in the generic extension is an extension of some normal measure of order 0 in the ground model. And we have only one thing that we didn't show, which is the claim that the intersection of W with V belongs to V. So I would like to give an argument for that. And here it's crucial, one of the properties of the forcing that we've stated at the beginning, the fact that the forcing does not add fresh subsets to both kappa and kappa plus, it's crucial here. And we can state this result in for many other forcings, not only for non-stationary support iterations of the forcings. So assume that P, let's assume that it preserves cardinals, not necessarily the forcing P that we considered so far. I'm saying something a bit more general here. So P preserves cardinals. Let's assume for simplicity that we have, okay, we can go without this assumption. it does not add fresh subsets to cardinals in the interval between kappa and 2 to the kappa is computed in V. So for our interest, 2 to the kappa is kappa plus. And let G be a generic extension. And in VG, assume that W is a kappa complete ultrafilter. Then W intersection with V belongs to V. So let's see why. So assume that, or let's say it like this, for every f, a function from 2 to the kappa is computed in V to the power set of kappa in V bijection. For every such f, we can define xf to be the set of all ordinals alpha below this cardinal. 2 to the kappa is computed in V, for which f of alpha belongs to W. And it suffices to prove that for some function f, the set xf belongs to V. So assume for contradiction that for every such f, xf does not belong to V. Now, this xf is a subset of 2 to the kappa as computed in V, defined in the generic extension, and it cannot be fresh by our assumptions. So let alpha f be the list such that xf intersection with alpha f does not belong to V. So we have such alpha f. The first initial segment of xf, which doesn't belong to V, and let alpha star be the minimum over all the possible alpha f's. So f as above. For every f bijection from 2 to the kappa is computed in V to the power set of kappa, we can define alpha f and let alpha star be the minimum over all the alpha f's, and assume that f star in V is such that alpha star is alpha f star. So we claim the following. This alpha star is below kappa. Before we argue that, let's see why it's enough. So assume first that alpha star is below kappa. And now we can define xf intersection alpha star inside V in the following way. In VG, we can compute the following intersection. And for every alpha below alpha star, for which f star of alpha belongs to W, we intersect the sets f star of alpha. Those are sets in W. And for every alpha below alpha star for which this doesn't happen, F star alpha is outside W, we take its complement and combine them in the intersections. Now this is an intersection of length less than kappa, and we can pick here an ordinal, beta. And by the way, our original argument didn't include this step. This is a simplification of Menachem Megidor. So we can pick an ordinal beta in this intersection, and then we can define XF intersection alpha star. XF star intersection alpha star is the set of all alphas below alpha star for which beta belongs to F star alpha. And this is the definition inside V, contradicting the choice of alpha star, contradicting the fact that alpha star is alpha F of alpha F star. So why do we have that alpha star is below kappa? So note that XF star intersection with alpha star has all of its initial segment in V because of the minimality of alpha star. So alpha star cannot be a cardinal in the interval between kappa and 2 to the kappa is computed in V, because we do not have fresh subsets for such cardinals. So alpha star is an ordinal, and we can use this, the fact that alpha star is an ordinal. Let's denote, let's assume that alpha star is above kappa. Our goal is to prove the opposite. So if alpha star is above kappa, we can denote by mu its cardinality. So we have the following picture. We have kappa, we have 2 to the kappa is computed in V. We have a cardinal mu and alpha star an ordinal with the same cardinality as mu. Now, we can pick in V a function which maps all the ordinals up to mu onto alpha star, all the ordinals above mu onto the interval between alpha star, all the ordinals above alpha star in a bijective way. So let's G in V be such that G restriction to mu for mu to alpha star is a bijection. G restriction to mu is a bijection, and G restriction to the interval above mu from there to the kappa above alpha star is a bijection as well. And now we can use this G, combine this G with the function f we had before, a function f from 2 to the kappa f star, from 2 to the kappa of V to the power set of kappa. So let's consider another function f, which is f star composed over G. Now, we may consider XF intersection with mu. This is the set of betas below mu, such that f of beta belongs to W. F of beta is f star composed on G of beta, So we have beta here, if and only if G of beta belongs to XF star. XF star is the set of ordinals which F star sends to W. And G of beta is going to be below alpha star. But we know that XF star intersection with alpha star is outside of V. And this is a definition by the minimality of alpha star. This does belong to V. So we get here the contradiction. Okay. So this finishes the first part with which is the characterization of normal measures in the generic extension. Are there any questions before I continue to the next goal? Okay. So let me briefly describe the structure of JW restriction to V as an iteration of V, and we will dive into the details next time. So far we have, or one remark before that. So we have the following correspondence, normal measures of order 0 on kappa. In V, we can translate them to normal measures on kappa in VG, in the generic extension. And if we want a unique normal measure on kappa in the generic extension, we need to start from a model where there exists a unique normal measure of order 0 on kappa in the ground model. For instance, models in which the ultrapower axiom hold, or the Mitchell order is linear. So under the assumption that we have a super compact which satisfies the uniqueness of normal measures of order 0, we can perform this forcing, this non-stationary support iteration of Prikry forcing. This super compact will be strongly compact. Again, we need to assume that there are no measurables above this super compact. We can cut the universe above the super compact if necessary. In the generic extension, we get that kappa carries a unique normal measure. So this was the original goal. And this, especially the K that we've defined before, led us to ask whether JW can be composed as to an iterated ultrapower of V without any more assumptions about V. We're going to assume that V satisfies GCH only. We're not necessarily interested in the context where kappa is strongly compact. So let's assume that kappa is a measurable limit of measurables and GCH holds below kappa. And let's describe the structure of JW restricted to V. So in our notations, we have JW restriction to V from V to M. W as the form U star for some U in V of order 0. Let's recall the original JW before the restriction. It's from VG to a model of the form MH. The situation here, and we have GCH. Up to kappa, kappa is the measurable limit of measurables. So we're going to describe the way JW restriction to V is decomposed as an iteration of V. Each step in the iteration is going to have a special role. It's going to add 1 point to one of the Prikry sequences in H for one of the measurables of M above kappa. Let me describe how it looks. So this K we've defined before from MU to M. This is the starting point. It hints that taking an ultrapower with U is the first step. So we start from our model V. We're going to take an ultrapower with U. So kappa is mapped to JU of kappa. And naturally, there are many new measurables in the interval between kappa and JU kappa, measurable cardinals. Now in M, JW of kappa is going to be at least JU of kappa. Actually, next time we will show the argument that shows that JW of kappa is exactly JU of kappa. It's not clear, but we will show that. We'll focus on that next time. In M, we're going to consider this interval. It carries measurable cardinals. For instance, the first measurable, maybe let's put it a bit higher. The first measurable above kappa in M. M should add, H should add a Prikry sequence for this mu. So let's describe this Prikry sequence, and simultaneously, this Prikry sequence will give us the first omega many steps in the iteration. So we may denote by mu0 the first measurable above kappa. In mu. This is the model mu. Let's denote mu by m0. The first step is going to be taking an ultrapower with some measure on mu0. We will describe this measure in detail, but the first step is going to be taking an ultrapower with a measure on mu0. This will result in a model M1. This will map mu0 to a measurable, which is the first measurable above kappa in M1. Let's denote it by mu1. I'm still not explaining exactly what is the measure taken on mu0, and next time we will state exactly how it is chosen. And in mu1, we're going to have the image of this measure. It's going to be a normal measure on mu1. The next step will be to take an ultrapower with it. And mu1 will jump to a measurable mu2. In continuing this way, omega many steps, this results in models mn for every n less than omega, and we have their direct limit, m omega. This m omega has the supremum of the mu n's produced this way. The supremum of the mu n's produced this way is going to be the least measurable above kappa in m omega. This measurable is going to be mu, the first measurable above kappa in m. This is going to be witnessed by the fact that after we got to m omega, the next step in the factorization of JW restriction to V is going to be by taking an ultrapower with the first measurable above this mu. So the next step will be to take an ultrapower with the measurable strictly above it. So continuing in this fashion, we're going to take an iterated ultrapower. As we take iterated ultrapower, we destroy measurables. Starting from mu, we destroy the measurables of mu by taking omega many steps until we get to a measurable. In one of the models in the way, we get to a measurable which has a Prikry sequence generated by the iterated ultrapower taken up to it. But this way, note that maybe new measurables are generated. So if we have in MU a measurable limit of measurables, let's call it lambda. When we take a measurable limit of measurables, it's going to stay measurable in each of the models taken in the iteration up to it. It's going to stay measurable because we're just taking ultrapowers with measures below it. What happens when we get to it? What happens when lambda is the limit of the critical points taken so far? This lambda does not have a Prikry sequence added to it by the critical points added so far. We're going to take a omega many steps, iterated ultrapower with lambda omega many steps as we took with this mu0, but note that when we do this, we generate new measurables. Once we take an ultrapower with such a lambda, which is a measurable limit of measurables, new measurables are generated below it. So, and for those measurables as well, we're going to iterate them in the same way. So if I have time, maybe I'll write the formal definition of JW restriction to V. Do I still have time for that? Something like 10 minutes?
I think that's fine, yeah. I just wanted to ask, so in the case where you have this measurable limit of measurables lambda, the iteration will not be normal from that point on, right? So the critical points won't be increasing.
No, we do take a normal iteration. We've always I didn't say that, we're always taking normal measures of order 0. Even on this lambda, we're taking a normal measure of order 0.
Okay, but the sequence of critical points, is it going to be increasing?
Yeah.
Okay, then I kind of misunderstood what you just said. I thought you have iterated up to this lambda, and now you create new measurables below lambda, and you take.
Then yeah, so the next step will not be the image of lambda; it will be the measurables between lambda and its image.
Oh, okay, but you don't have to go below lambda. I see. Okay, all right. Thank you.
So maybe let me. I think if I'll write this in a bit more formal way, this will be a bit more clear. So we can define, not inside V, but inside VG, an iteration M alpha. Let's denote by kappa star the image of kappa under U. And we will later show that this is the image of kappa under W. So we define an iteration M alpha for alpha less or equal to kappa star. M will be M kappa star eventually. Simultaneously, we define, so those are models. Simultaneously, we define those mu alphas, those critical points of the iteration. It's going to be an increasing sequence. We're going to describe a normal iteration for every alpha below kappa star. And I didn't describe the measures on mu alpha. I'll describe them in a few minutes. U mu alpha measures on each of the mu alphas. So each mu alpha is going to be measurable in M alpha, and U mu alpha is going to be a normal measure of order 0 on mu alpha, which belongs to M alpha. And in successor steps, M alpha, or before the successor steps, let's define M0 as before to be the ultrapower, to be MU. mu0 is the least measurable above kappa in M0. What about U mu0? So I'm going to cheat here a bit. When I define the U mu alphas, I'm going to give an external definition. The fact that this U mu0 belongs to M0 is not trivial. U mu0 can be defined using K. We can take all the subsets of mu0 such that mu0 belongs to their image under K. And we consider only subsets of mu0 in M0. It's not clear at all that U mu0 belongs to M0, but this is the case. And the board is stuck. So I'll provide the details next time, but let's see how the iteration is proved after stage 0. So if alpha is limit, M alpha is the direct limit of the previous M betas. So a direct limit is taken. And for every alpha, let's consider the model M alpha. Assume that M alpha has been defined. We now want to construct M alpha plus 1. So M alpha plus 1 is going to be the ultrapower of M alpha using the measure U mu alpha on the measurable mu alpha. But what are they? So first, mu alpha is the first measurable mu in M alpha, measurable in M alpha, such that it satisfies two things. So mu is greater or equal to the supremum of the sequence of the mu betas defined so far. But sometimes we skip this supremum. For instance, after omega many steps, when we had this limit of the mu n's, at stage omega, after stage omega, we didn't want to take an ultrapower with it. We want to take an ultrapower with the first measurable above it. In general, we need mu's which have cofinality above kappa when computed in V. What are those mu's? We at stage M alpha, we get to the point where we meet such mu, which has cofinality, which is greater or equal to the supermum, and has cofinality above kappa in V. So for such mu, we're going to need a Prikry sequence for its image under the embedding from M alpha to M that we will define. In order to generate such a Prikry sequence, we're going to need to take iterated ultrapowers with mu and its images omega many times. What about mu's which don't have cofinality above kappa, but have cofinality, or are there such mu's which are measurables in M alpha, but have cofinality between omega and kappa in V? Do we need to consider such mu's? So one of the things we showed in this work is that if we have a measurable in M alpha, which is above this supremum, strictly above the supremum, then it has cofinality above kappa in V. This is not something which is related to the forcing. This is a general result about iterated ultrapowers. But if we have mu, a measurable, even inaccessible, by the way, in M alpha above this supermum, strictly above this supermu, then it has cofinality above kappa in V. So there is a simpler description of the mu alphas. We don't need cofinality of mu in kappa in V above kappa. It's enough that the cofinality is above omega. And once we have this mu, we can define mu alpha again outside of M alpha, all the subsets of mu alpha such that mu alpha belongs to the embedding. I didn't define the embedding from M alpha to M. Okay, so next time I'll provide the exact definition of u mu alpha. U mu alpha in M alpha will be a normal measure on mu alpha, and the M alpha plus 1 is going to be the ultrapower taken with it over M alpha. Simultaneously, as we define this iteration at stage alpha, from M alpha to M, we will have a quotient embedding, K alpha, from M alpha to M, a kind of a generalization of the K we've seen before. And this K alpha, we will prove, not in details, but at least I'll try to convince you that the critical point of this K alpha is this mu alpha. It's not clear at all that the critical point of K alpha is measurable in M alpha. So it is going to be measurable in M alpha. It's going to be this mu alpha. The measure U mu alpha derived from it, a measure on mu alpha derived from K alpha, indeed belongs to M alpha. And then we can take M alpha plus 1 to be the ultrapower taken with this U mu alpha. And this construction stops after Ju kappa, which we denoted by kappa star, after Ju kappa many steps, and results in the model M. And after we have a full description of this iteration, we can talk about definability of the restriction of JW to V as a class of V. Okay, so next time I'll continue from this point, give more details about the iteration. Are there any questions or remarks?
I have a sort of a simple-minded question. Early on, you're assuming GCH. Could that, I mean, just to know, could that be simplified to 2 aleph alpha less than or equal to aleph alpha plus 2 or something?
We need in MU, we need the 2 to the kappa to be kappa plus. We didn't show entirely how we use that. So one place we did use GCH today was that okay, I didn't show how we used that at all, I think, today. We need GCH in several places. So for the fact that kappa, that there are no fresh subsets of kappa in the generic extension, we use their GCH. We need GCH when we argue that the critical point of this K is measurable, is the least measurable in MU above kappa. I hid really well the places where we use the GCH, and I'll try to emphasize this next time, but we do need GCH. It might be enough that U concentrates on places where GCH holds. So we have GCH in MU.
Mm-hmm. Thank you.
Okay, very nice. Any further questions? Okay. Seems like everybody is satisfied. Yeah, it was a great talk. Very nice, very interesting stuff.
Yeah, thank you very much. Super interesting and really, really nice talk.
All right. Great. Thanks a lot, and see you guys next week.
See you next week. I'm looking forward to it. Bye, everyone.
Bye-bye.
Bye.
Bye.
Bye.